Understanding how storage works in Solidity is crucial. It is crucial as a programmer to understand where do these variables go that go into storage, how do we load variables from storage, and it's also important to understand for security reasons. In fact, a lot of hacks can be done by understanding storage as well, and defensive programming can therefore be performed to avoid that, access is not granted to what you don't want. So storage is absolutely critical in Solidity. It's also the most expensive operations, is really storing a variable and loading. Like, these are among the absolute most expensive operations. So understanding that for gas efficiency is important as well. So let's dive into storage. The way we're going to do that is we're going to look at 3 examples. We're going to start with a super simple example and just discuss the storage layout. And then we're going to go into a more complex example where we have a mapping. So it's more of a dynamic type where we don't know when we create it how many items will be added in the future, and it affects how we're going to lay that out in storage. And then the final example, we're going to look at nested mapping. So it's a mapping within a mapping, and we could technically keep going. So I'm going to teach you kind of how to think about how to access where these elements go. And we're going to have some nested mapping with a struct even. And that's actually the example that they use in the Solidity documentation, kind of as all right, once you understand this, you pretty much understand how storage works. We're not going to touch strings and bytes, although they're slightly different than the mappings and the dynamic types we're going to talk about today. But you'll understand them easily once you get these points here. Let's really dive in and understand how storage works in Solidity. Welcome. Let's take a look first at a simple example here. This is going to be part 1, and we're just going to be storing simple types here. So, a uint or something like that, an address, etc. But first, I just want to make sure that we both have the same visual of what the storage looks like. So you can think of the storage layout in Solidity as being this extremely large number of boxes in this array. So these are just elements in an array. There's an element, there's another element. And they just all are initialized with 0. And the index of the first box is 0, the index of the second is 1 and 2, and then, of course, I don't have time to write out this many boxes here, so I just do ... and then we get up to a total of 2 raised to the power of 256, and then minus 1. That is the total number of potential storage slots you can use. This is an insanely large number. It is, I wrote it out, it's this number here, and that essentially corresponds to, or is on the scale of pretty much the number of atoms in the visible universe. So you have plenty of storage. Of course, a note here. Does that mean that each client, when they run an Ethereum node, are storing this many buckets on their hard drive? No. It does not mean that, because that's just not possible. First of all, you need, let's just say each was 1 bit. You need this many bits just to store it on your machine. You don't have that amount of space. Nobody does. So no, it's not like that. It's more intelligent, which is also why the sstore and sload work the way they do. But basically, it's only bins or only buckets or slots. They're also called slots. It's only slots that have some data in them that's non-zero that are tracked. Okay, so it's kind of a very efficient way to track that. But you can think of it like this. You can think of it having access to this, and you can certainly go to any bucket you want and put whatever you want. So I can go to storage slot 1 quintillion and put 1 in there. That's fine. That's doable, and it will just track that 1 bucket. Okay, so that's how it's done and tracked. So all right, with this, let's start putting some values into these buckets. Okay, so what I did was create a simple code over here where you can see that right here, you have a uint x, you have a function to set that x. Here's the new x coming in, and this sets the existing value of x, which is a storage variable. You can see it's defined at the contract level here, and it sets that storage variable to the new x. And then I created a function here. This is a helper function for us, and it's just going to be able to read any storage slot that you give it. So that's what this I is. It's just the index. So I can be 0, you're reading from the 0th storage slot, or it can be a quintillion, and you read from the quintillionth storage slot. The sload is a special command in fact in Yule, because you see here we're in assembly here, so that's actually we're writing in Yule. But sload loads what sits in that slot and gives us back the content, or the value, if you will, of what is in that slot. So to give you an example here, sload is just a way to load things out of, let's say, the fourth bucket. Let's say that the fourth bucket sits, there's no point in necessarily jumping there, but let's just say we do that and then keep jumping. All right, so loading from bucket 4 just says, give me the content of what sits in bucket 4. So we can visualize it like this. We can go to bucket 4 and we just do that. There you go. Give me the content that sits there. So whatever value it is, right now it's 0, and it will be 0 for anything you ask it of, unless of course you put something there. So that's all it is. And then sstore is the opposite. So sstore into this bucket will store a new value in there, okay? Let's try this out. Let's compile this code and let's deploy it, which is easy. We'll just deploy in the VM. And we can actually try to, first of all, read the storage of slot 0. So what we're going to do is say what sits in slot 0. And we can confirm that there is a 0. You see here? So it always returns a bytes 32 here when we read the storage slot, because that's what we told it to. So it'll just give you a bytes 32 back, which is 256 bits, represented as hex here. So you see the 0x and then 00. So you can read storage 0, you can read storage 1. When your contract is first deployed, there's nothing in any of these buckets, unless, of course, in the constructor you've said something, but we haven't. So, you can ask for any bucket you want, even a very, very, very large bucket. All right. So you can just ask, what is the storage there? Everything will be 0. So far, so good. Let's set a value of x, and x, my first question will be, where in storage does this sit? We already know which storage slot it's associated with. We know that. And the answer is, because it's the first declared variable here in the contract, it's going to start occupying, Solidity will start occupying the storage slots starting from 0, which makes sense, right? In lack of a better start. So basically, x is associated with the storage slot. Okay. So whenever we set x to some other value, we're actually going into this bucket and setting it. So we can set it to 2, and we can read slot 0, which is associated with the x, and we should get back a 2 here. So when you read the storage, you see we get a 2. We can also read storage slot 1. We can see it's not affected. It's still 0, and any other storage slot will be 0. So far, so good. We haven't done anything crazy. We've just put a 2 right here. Cool. So that's good. One thing to note is that Solidity also uses packing of variables. So if you, for example, do this, you have this is, by the way, a uint256, right? This is synonymous. The two are the same. But if you have y and z, both uint128s, it means that I can actually pack these together, y and z, and to fill up the 256 bits that is one slot, right? So each of these slots can hold 256 bits, or 32 bytes, if you will. If you go over that, you have to use more slots, basically. But in this case, we can actually do packing as well. So we can say, x sits in slot 1 because it takes up all 256 bits, so we can't do anything about that. It takes up the whole space. If you go to slot 1, you'll definitely find y because it can fit there. It's less than 256 bits. But it's not going to be slot 0, slot 1, slot 2, because z will go in and be packed with y. Solidity is clever enough to pack them together because it realizes that y takes up half the slot, z takes up the other half. So we can actually go in here and we can just say that half of this slot can be put as y, and the other half can be put as c. So half and half. And basically, yeah, that's where they'll sit. So y and z. Yeah, this was x and so on. So you can see like you can actually pack variables, and you can pack many more variables if they don't take up a lot of space. So anyway, just be aware of that. Yeah, we can test that actually. Let's test that as well. So we can set x, but we can just generalize that to do this. And we can set z is near z. All right. And we can give an x, and we can give a uint128 new y, uint128, and we can say new z. All right. And we can just say set or something. So let's redeploy this, deploy this, and we can read the storage slot of 0. There should be 0, right? We haven't done anything. And 1 should also be 0, just to confirm the starting condition. Oh, this changed name. Sorry, I think I clicked the button. All right, so now we'll actually deploy this and try. So we'll reach storage of 0, which is 0. We'll reach the storage slot of 1, which is 0. So the starting condition makes sense. We'll now put a 2 for x. We'll put a, 3 for y, 4 for z. So let's set those variables. And now let's read the store slot 0. As mentioned, only X can fit in slot 0 because it already takes up 256 bits, as you can see. So we will read the storage, and you can see only 2 sits there. That's fine. But now the interesting thing is, when we reach slot 1, we expect it to actually hold both Y and Z. So we'll take a look. Indeed, it does. So you see that Y actually sits in the kind of the lower bit, like least significant bit piece, and then Z sits in the higher. So kind of like we had drawn over there. So Y sits to the right, Z sits to the left, so to speak, if you will, from least to most. So you see it only takes up half and half, but they're packed together. And if we go to slot 2, where we would, if we didn't know about bit packing, or if we didn't know about storage packing, we might have thought that Z would have been sitting here, but it doesn't. Okay, so that's just a little note on that. Now that we rock the storage layout and simple storage variables, let's go to a more complex example. Now we're going to talk about a mapping. So keep our U index, it doesn't really matter. It's just to show that something a little bit more interesting. And then the mapping is going to go from a UN to a UN. So again, remember that's a UN256 to a UN256, and then we're going to call the mapping M. The storage layout is going to be the same, so just ignore all the arrows for now. The layout will be the same, but the question is, where are these variables stored now? Where is M is mapping? So let me give you an example. This means that M, one syntax for M could be, store in key 2 the value 4. You can use the mapping like that, just the usual mapping. The question is, where does this 4 sit in storage? Where does it sit? That's what we're going to find out. So the way mappings work are as follows. In this case, and with this layout here, X will take the first storage slot, so index 0, and the mapping M will take slot 1. Okay, so that's how it is laid out. Since we don't know how many elements will ever be in the mapping, right? The user can do whatever, the contract can exist forever. We will never know. So, we can't just start adding things from storage slot 1 onwards in general, because what if we had another variable right after it called uint y? It would need to sit in slot 2, or like at least sit in the first slot after the mapping. Since we don't know how large the mapping will ever be in general, we don't know where to put y, because it's like, maybe we have a mapping of 2 elements. Great, then we just put y in, 0, 1 to the third slot, right? And if it has one more, well, just put the 4th. That's fine. The problem is mapping is dynamic. M can just keep changing. So Solidity would keep having to move y and any other number of variables after that, keep pushing them out in storage all the time, which would be very inefficient, very silly. So the design instead is to say, since we don't know how many elements M will ever hold, we're actually just going to start putting them somewhere else in storage. Okay? So how does that work? In this case, X sits in storage slot 0. Let's say it takes a value of 2. We're going to put 2 there for X. Okay, let's say we do that, like that. 2 is going to sit right here. That's fine. What's going to sit in storage slot 1, where the mapping is a 0. We're just going to have these zeros. And by the way, I didn't mention this before, but I just drew a bunch of zeros in here. It's understood, or it should be understood, that these are 256 bits of zeros or 32 bytes of zeros. One zero seemed too little. I did want to draw all of them, so just so you know, there's nothing particular about this number of zeros I drew. They're all zeros, just like you saw in our example before. Anyway, so the mapping here, it just sits, nothing is put in the slot, it remains 0. Okay, even though the mapping sits there, nothing is stored here, it just remains 0. That's how the mapping is stored. To then get, let's say we just want to store a key, like 2 is the key and 4 is the value, so we're storing into this mapping, into its key 2, we're storing the value of 4. Where does it end up? This is where you find it. So if we do this, M of 2 equals 4. The way the bucket in storage where this 4 sits, we can find by hashing. So we can use the check 256. I'll show you an example of the key with the slot. So the key will be 2, because we just used 2 here. And the slot is important as well. That'll be 1. So it's actually important to know where it sits. So even though we're only storing 0 in here, it seems like it's not doing anything. Well, the index of the bucket is important, and that will never be packed together with other variables or done anything. No, this bucket belongs to this mapping, and the index is 1. So that's it. That's our bucket, and it's important because we use it here to actually hash it. Okay. Why do we do that? Well, what if we had another mapping right after it? Let's say we had a mapping N that looked exactly the same. We could totally have that right here. And this would then now sit in slot index 2. So now we would hash, and let's say you did n, you also did n of 2, you're free to do that, n of 2 equal to 4. If you just did this, but you didn't respect which slot it sat in here, then what would happen is they would hash to the exact same value because you would only hash the key. Okay, you would say hash key equals to 2 without the slot. And they would go to the same bucket and they would collide, these two mappings. So that's not good. So we need the slot, and that's why it's very important. The slot is very important for a mapping, even though only 0 sits there in the value. Okay? So to get the location of this 4 here, we're gonna hash the key 2 with slot 1 for this m here, okay? And that gives us some number. It's not this number, I just wrote this as an example, but it's some large number in general. And then 4 sits there. We're gonna get the exact number in a second. In fact, right now. Now we have that same layout. We have x, we have m, okay? And we can just put x equal to 2 to start. That's fine, just kind of like we did in that example in Miro. And then I have a function that can basically add things to m. So you see here, you give it a key and you give it a value. So all it does is just go into m, kind of like we did m of 2 equals 4, for example, if we use 2 and 4 or whatever. So I can just store things in the mapping. I still have the helper function to read storage, to read any storage slot, so that'll become helpful. And then I have this new function here, this new helper function. This helper function is the hash of the key with the slot. So this helper function is exactly what I meant by this. Hash of key with slot, which was 1 for this example, right? So that is what this function does. The hash is just another name for this. I mean, this catcheck256 is a hashing function, so it's just a hash. API encode is needed because you need to put these two 32-byte values together. You need to kind of concatenate them. So API encode does exactly that. Note that in general, you shouldn't use encode packed because encode packed is trying to really pack only the bits necessary together. So you need to use encode. And then you need to give the key and, as mentioned, the slot. So this mapping slot is this mapping slot is what I call this, like the slot that the mapping sits in, 1. Okay? And then the key is whatever key we used up here. So it's a key in the mapping. All right? Let's try that. And then you get back, by the way, the slot. So like you get back the slot that the value should sit in. The value that sits under this key in this mapping that sits in that slot. That's what comes back. All right, so let's try this. So let's deploy this. We're gonna take a look first before we do anything. We're gonna read the storage of 0. We expect a 2, and we get a 2. That's because we set x2 2 here. M sits in slot 1, so we can read slot 1. Again, just because the mapping sits there, like it's still important, but there's just a 0 there. So, but don't get thrown off by that. Now let's try to add something to M. So let's try to add key 2 value 4. All right, so let's add that to M. Read store slot 1 is where the mapping sits. Let's see what happened. Nothing. It's still 0. That's fine. That's what we expect. But the question is then, where did it go? Did it go to the next slot over? No, it did not go. So where is this 4 sitting? It's not, we just stored it. Where is it sitting? So that's what I'm saying here is that it doesn't sit in slot 0. It doesn't sit in slot 2 and so on, or 1 or 2. It doesn't sit there. We need to do this hash of the key with a slot. And that's what this function does here. That gives us the slot of where 4 sits. Let's try that. So we can get the location of the mapping. The mapping slot we know is sitting in 1. The key is 2. We can get that location. So this is the location. This is the slot index where it sits. So to update this over here, we need to go out into storage somewhere. As you can tell, very, very far into storage, like insanely far into storage. Okay? This is the index of the bucket of this bucket. That's the index of the bucket. Just like this is 0, this is 1, this is 2. This is just an unfathomably large number. That's that bucket where this number sits in. Just happened to be. All right? So we can now take this number. It's just a number. We can go look at what sits in that storage bin, right? And we can confirm that 4 sits there. So we're going to read this storage and look at that. 4 sits there. So that's where they're stored. So why are they throwing these values all the way out here in these crazy high bins? Well, again, because of this collision issue. Like you never know how many items will be there. So you kind of just say the number of buckets in storage is like almost the number of atoms in the universe. So like a collision is so unlikely. So we'll just start throwing darts at this huge array and just, completely random darts. And just start putting things in there. Note that it's not even consecutive. It's not that if I then put it's not even if I put m of 3 equals whatever, a new number 5. If I do this, it's not that this will then 5 will be stored right after. No, it's just going to be a completely other random spot. Let's confirm that. So we can actually add now 3 and 5. So I'm adding a new key 3 with the value 5. I'm going to click here. Let's just confirm that the storage is not altered from before. Of course not, it shouldn't be. And let's in fact go to the next bucket over. We're going to go one bucket over and see, is the 5 sitting there? So we're going to change this to 8. I just moved one bucket over to an 8. I moved one bucket over. Read. No, it doesn't sit there. So they're not storing it consecutively, right? So let's try to get the location. Again, we use the same mapping slot when we now get the location. I'm going to call this function to get where it actually sits, this 5. The mapping hasn't changed. It still sits in slot 1. The key is now different. It's a key of 3. I'm going to get the location. Look at this. It sits in this bucket here. It's a completely different bucket. So that's maybe this bucket or something. So we're going to say 5. And this is the new number. Okay, whatever. It's just another number. I can't even see if one is larger than the other. Yeah, this is actually smaller. So it doesn't sit here. It sits somewhere here. Still a very, very high number, right? Like very large number. So that sits right here. So the mapping just, again, it just is just throwing darts at this storage array completely randomly. Generally very large numbers, of course. So yeah, could collisions happen? Technically, but it's just exponentially low probability. By collisions, I mean, what if you have a bunch of other mappings and they just all start throwing darts at this storage array? This stores here, that throws here. Well, sure, but the probability is like 0 basically, right? Like practically 0. So that's how our mapping works. So I hope that kind of helps a little bit understanding that they're just completely gets tossed to these random locations. And here's the code for how to get the slot that the mapping ends up in. And here's the code for reading this. All right, cool. So in part 3, we're going to understand how nesting mappings work. So we're going to have a mapping that maps from a uint. That's the key. And it used to map to a value of a uint, but now it maps to another mapping, which in turn maps from a uint to uint. So, and you can keep going here. You can nest these mappings as much as you want. But what I want to do is just make sure you understand that it's okay, that it doesn't actually complicate things, because you just recursively apply the rules that we just went over. So let's take a look at this. We have a mapping n this time. And again, it's mapping from a uint. So n of 2 is the key, to another mapping, which maps from a uint to a value. So that's why we actually need two of these brackets now. So n of 2, great, that's the key 2, maps to another mapping. So we're going to now store something in that mapping's key. The key is 3, and the value is 4. So you need to kind of nest this like that. N of 2 of 3 equals 4. So where does this value 4 sit now? Where does it get stored to? Well, step 1 is we can find the slot where n of 2 is, which is the start of the next mapping. So at least we can find the start of the next mapping. And if we had 5 mappings or 10 nested mappings, we would just keep going like that. Find the start of the first mapping, of the second, of the third, of the blah, 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 and so on. So we're going to hash, since it still sits in slot 1 here, we're going to hash key 2, if this is the case, like n of 2 of 3. Key is 2 with slot 1. That gives us this bucket here, or in fact, the other number we had up there, but this is a random number I used. But we're going to get the start of the next mapping. So now we just kind of reset, if you will, like that's the recursive part. And then we forget about the old mapping and we just say, great, now we're standing in a bucket. We know there's a mapping starting here. So we're going to hash the key 3, because that's the next key, like that's the key in that next mapping, with whatever this slot is we're sitting in. Again, it's not going to be this exact number. It's going to be another number. But anyway, key 3 with that slot. And that gives us where the value sits. Okay. And of course, you can combine all these into one, right? You can just combine this hash with that hash into one big hash, because you already know all the keys in the nested mappings, 2 and 3 up front, right? But I'm just trying to break it into steps. So let's try to do it one step at a time. So we're going to go to 3 nested mappings. So you see we still have X. I don't know. I'm just keeping it around to like make it more interesting. And we have this nested mapping. So we're mapping from a uint to another mapping from a uint to a uint, okay? And we can add things to n. So we can just say key 1 and key 2 is equal to a value. Okay, and then we can these are the good old helper from before. These have not changed. You can get a location of a mapping, and read storage slot. Again, we could generalize this to get a location of a nested mapping just by concatenating those hashes. Like we'll just take this hash, right? This hash as the slot down here, and you can directly jump to 4. You don't need to do 2 steps, but I just want to show you how you can iteratively think about it. All right, so let's deploy this. We just need to compile it first. So compile nested mapping and then deploy it. So cool. So we can read storage of 0. Let's just confirm everything is working fine. Yeah, great. So then we can add to n. So this time we need to give 2 keys. So let's give 2 and 3, just like in the example, and 4. I think that was the example. 2, 3, and 4. Yes. So now we're going to add that to n. Great. Now that sits in n. Let's still read the storage of 1 here. Nothing should be sitting here. That's the first mapping started, right? Nothing sits there as we know now. But we're going to get the location of the mapping of the first keys. We're going to look at mapping slot 1. The mapping sits in slot 1. This is what that means. And the first key is key 2. That was the first key we put. So it tells us the bin or the bucket is this. So this number here is in fact this number rather. Okay? Very large number, as we already touched on. This also means that we're gonna put this as the slot. So to get now we're sitting in this green bucket. We found the location of the green bucket, which is the first or the outermost mapping, if you will. Now we're gonna go find the innermost mapping, which actually happens to hold the value. To do that, as indicated here, you need the key of that mapping in there, which is 3, and the slot is this. So let's copy this, and let's put that here, and we're gonna get the location of what slots does it sit in? This is a slot. What's the key? 3. Okay, get the location of this, and this happened to point us to. And by the way, so this is I'm just gonna show you here. This points to this index. This is the key of the yellow. This is where the value sits. Okay, and again, this is actually less. You see here, I'm kind of comparing. This is actually less. So this drawing is a little bit misleading because this 4 is actually sitting before the green box, but it doesn't really matter. It's just it's just general drawing here. But now we expect 4 to sit in this exact slot index. Okay. And again, if we had more nested mappings, this would be the start of the next one, and so on and so on. But let's see. Let's confirm. Let's read the storage slot of this, and we expect to get 4 in return. And you see, we get 4. So that's how we can read from a nested mapping. Let's jump to the last example. The last example is actually taken from the documentation, Solidity documentation, and it basically has this contract, this simple contract, and they're asking, given this layout, you have a struct, you have a uint, you have a mapping, where is data of 4.9.c? So like it's a nested mapping, so the first key is 4, it's a uint, it goes to another mapping which also maps a uint, so that's a 9, to a struct s, which has a, b, and c as its parameters. So they're trying to get data of 4.9.c. So now we should actually know how to get that. First of all, a little comment here. When you define a struct here, when you just define it and don't set it to anything, this doesn't take up any storage. So it's not like this s is sitting in storage slot 0, because there is no s initialized. It's just a definition of it. uint x though does sit in storage slot 0, and the mapping data does sit in storage slot 1. So that's important to know. Great. So let's reason through this. So we have the struct uint this and this n, and we are interested in finding, let's say someone put in 2,3, they put this s. So this is kind of where this s sits, which might be 1, 2, 3 as well. Like let's say the struct sits here. Structs in Solidity, because they can be computed ahead of time, like Solidity knows exactly the layout of A, B, and C, like how they should lay out. They actually are laid out consecutively. They're not a dynamic type. I mean, they can hold dynamic types, but they're not like themselves. So the point is that this will actually be consecutively stored. So anyway, we know how to get there, right? Because we know how to get from the first mapping to the second mapping. We just take the key, which could be 2, with whatever slot the first mapping sits in, and we end up here. Great. Now we're on the second mapping. We know what slot that sits in. We know the key is 3, and that brings us over here. And that brings us to the start of the struct. So the struct will be whatever A, B, and C is. Like A will be stored here, because you can see, in fact, A and B will be stored together in the first slot, right? A and B will take up 1 slot because you can pack them together, as we mentioned earlier, because 16 plus 16 is less than 256. The second slot will have C sitting in it. When I say second slot, I mean relatively to where this started. And then, that's it. So C sits right in here. So let's confirm this, and that's it. So we're going to go to the nested mapping example. We are also going to compile that. And then you can see here the layout. Struct S, it has A, B, and C. It has X, and it has this data array. We can set C here with the function that I wrote, so we can give you key 1, key 2, and it'll always set it'll always set C, and it'll set it to this value. And we can still read the storage slot and still get the location of the mapping, just like before. Let's deploy it, and let's start by setting C. So we can set it under 2, 3, and then we can set the value that we want to store in C as, again, maybe let's use another number, 8 or something. Set C. So we have stored, and by the way, this is called data now, not N, but we have stored in data under 2, 3, we have stored this S, and we have used the value. We haven't actually set A and B, so those will be 0, but we've set C to 8, okay? So the first thing is hash key 2, because that's the first key, with slot 1. So we're going to do that to get the first location, right? So the mapping slot is 1 and key is 2. That's the order of the input. So this is the location of the first slot. And you can kind of see these locations, of course, always the same because you're hashing the same number. So like as above, these will always be the same here when you use the same keys and slots, right? So anyway, so this number now also needs to go in here, right? So we know this now. But now we're going to use a key 3 because that's the next key. So great. So we'll do this number is the slot with key 3. We'll get the location of the next one. And again, this is actually technically said before, but we're just going to ignore that. But anyway, this location here, like this number, is where this is where this slot starts. That's where the struct starts. Okay, like that was the output of this hash. So that's where S starts. And so we expect to find A and B packed together in this location. Of course, they're both 0, so we don't expect any value here, but we can get the location nonetheless. We can read the storage slot nonetheless to be 0 as expected. But now, if we go to the next one, so we just add 1 to that location, because again, this is consecutively stored, the struct, because there's nothing dynamic about it. Solidity knows exactly which slots will ever be taken up by this struct. So we just need to increment by 1, and we should find an 8 sitting in the slot 1 over. So we're going to read the storage of not 5.5, but 5.6, and we expect an 8. And there you go. There's the 8. So that is the answer to the documentation's question, basically, where is data for 9.c. So I hope that you understand in depth now how this works. Dynamic arrays is another topic that's similar to mappings, but there are some differences. So for a dynamic array, you also don't know how many elements will ever be added to it, but Solidity handles a little bit differently.